microphones again, so I'm just going to ask a question. So I do have my other microphone there. I'm hoping that it works. Right. Yeah. Yes. Awesome. Thank you very much. Okay. So let's start today with a quick recap of what we did last week. So we're just going to go over, make sure that everybody can just remember what we did last week, and then we'll start with a couple of examples, looking at some PCBs which I wanted to show you last week. And then we'll start with an introduction to EagleCAD, which is really great. So let's not waste any time and jump straight into. So I'm going to share my screen, and we're just going to go over the presentation very quickly once again. The presentation which we did last week. And as a so like a preview, so this week, today we'll be, like I said, we'll be looking at some PCBs that I made, some components, some soldering, and then we will move on to the introduction to EagleCAD. Then later on, we will start with the simulation, how to do simulation in EagleCAD, and we'll do it for analog and digital circuits, which is, I think, really great. And then from there, we will create more complex circuits and then transfer those circuits to a PCB format, which is then ready for manufacturing by yourselves if you are able to create PCBs, or by a manufacturing company. But we will look at that as well. And then hopefully, if we have time, like I said, I will create a PCB with you guys in a project that I'm interested in, and then I will order it, and then hopefully it'll get here in time, and then we can have a look at it and sort of compare it between what we have designed, what we actually got back, and also everything surrounding that process, so that by the end of this course, you should be able to design your own PCBs and also have them manufactured. And hopefully we'll go through some tips and tricks of how to make sure that what you design is actually what you get in the end. Because it is quite difficult to start with, meaning that, let me just see, I've got this, meaning that it's, you have to specifically choose all of the components that you want to use, because all of these components are different sizes, and we'll also look at how to determine the correct size of components and make sure that what you order and what you get actually fits on your PCB. And that is relatively simple, but we'll talk about that as we get to that. Okay, so I'm sharing my screen. You should be seeing my generic Windows screen background. And just quickly, like I said, we'll just quickly run through the presentation once again. And as you guys have done already, and you're very good at, if something goes wrong in my presentation, like it did last week, where there was no sound, or I don't know, I do not share my screen when I think I'm sharing my screen, just let me know, as you guys are already doing very, very well. So, right, as you should all be able to reach me via this email, quite long email address. And like I said, if you have any questions, anything at all, just let me know. And like I said, the idea behind this course is that you should be capable to design your own PCB with some design elements, as we'll speak about as we go through this theory part of the course, and also as we then try to implement those theory elements in printed circuit board design. We talked about what a PCB is, the printed circuit board. And I said it's an electric circuit made up of conductive material and a substrate, as the substrate is the non-conductive material that forms up the base of the printed circuit board. And then we spoke about the different materials that you can select for the specific board, and we spoke about why copper is mostly used, mainly because it's very cheap. It is very abundant, meaning you can find it everywhere. But then we also spoke about the physical properties of gold and copper. And we also spoke about why the chemical effect of tarnishing, what that does in elements like silver, and then how that affects electrical conductivity. And then we also spoke about that tarnishing is a relatively thing that you do not want in your PCB design, because it affects the electrical characteristics of your board in a negative way, and then just changes the properties. And as we spoke about the PCB, when we design our circuit, we want our properties when we first make our circuit to remain the same, because especially as I keep on mentioning, with high frequency digital circuits, you would like to have that characteristics remain it's the same throughout its lifetime. I introduced the term traces or tracts, meaning the physical connection or the physical copper lines contained in the PCB, and I'll hopefully show you a couple of traces today. And we spoke about silver, copper, aluminium as well is also something that you can use, and sometimes it is a little bit, it replaces copper, but more of the time, or more or less, you will almost always be working with copper. We spoke a couple of elements of a PCB and a couple of components. And then we spoke about trace width and how that width corresponds to how much current it can carry. And we spoke about current carrying capacity as a function of the physical dimensions of the trace, and that relates back to a lot of the times between the heat dissipation of your circuit. And in PCB design, this is a very major theme going throughout your designs, is that you will have to know how much current is running through any specific trace, and how much current it might expect to see even in a short circuit. Because the current running through a conductor, in this case a trace, it will have a power loss. And in most cases, that power loss is in the form of heat. Now, heat is a very interesting sort of characteristic in a circuit, because heat can then be dissipated throughout the board, meaning it can spread through a board. So even if you have one trace that heats up, that heat can then spread to other traces and then spread your heat throughout your whole board, heating the whole thing up. So even if you have one trace that is heated up, it can spread to your other traces. But what does heat do? Well, if it's a handheld device, like let's say a mobile phone, it might be uncomfortable to hold in your hand, and also it might burn your the user's hand, which is not a good thing. What also happens with heat, if it gets warmer, the physical trace, the copper, might start to melt. If the copper starts to melt, it will degrade and then not have the same properties as you had designed for it. And that's like a relatively worst case scenario, that copper might melt. Now, electric circuits, they do heat up quite quickly, even if you're dealing with relatively low voltages, especially high frequency circuits with integrated circuits or microcontrollers or processors, they tend to heat up. Now, what might also happen is that if you have your printed circuit board, and you have to understand how they are made, you have the substrate, which is a fiberglass or some sort of resin, and then the copper is like placed on top of it, not like glued on top of it, but just placed on top of it, so it is attached to the substrate. Now, what might happen, especially if you're using cheaper boards to save on costs, is that the copper might heat up to such an effect that it separates from the substrate of the board. Now, what then happens is that you have your very thin trace of copper separated by a space to your substrate, and then quite often what happens there is that the trace then just simply breaks, which then also creates a break in your circuit and then stops it to functioning. So heat can affect your board in a lot of different ways. And now the trace melting or the trace separating from the substrate are extreme cases, but it is something that you will have to keep in mind. And there are methods of failure that your PCB might endure, if I can say, form it like that. Now, you will also be, usually you will be testing your boards. So when you will have a PCB made, you will not make 1,000 straight off. You will create like we called prototype circuits. You'll start with simulation, move on to breadboard, then maybe a strip board or a Vera board, and then to PCB, and then you'll test that board. And you'll perform certain tests under certain loads to see how your board performs, taking physical readings, and then you'll have to inspect your board like we're going to be doing here under a very, very simple microscope, which I've been trying to get into working for quite a while now, and it finally does. But a lot of the Eagle tools would give you will do the checks themselves in terms of how much heat is generated by your specific circuit. So we'll look at the tools inside Eagle that you can use so that you do not have to calculate everything by yourself. So I'm sharing my screen once again, and we will have to remember that this is all that you will have to designate how thick your traces are, and you will have to understand how much current it can carry. And you will probably go back to a table like this, which will then tell you how much current can your trace carry. And we spoke about this as a certain a schematic for a circuit. Now, there's another term. The schematic is the symbolic representation of a circuit, and that is the first thing that we'll be creating in EagleCAD, and we will be symbolically recreating certain circuits or certain elements in our electrical circuits, like resistors, transistors, capacitors, and integrated circuits, and they all have their own symbols, which we will also see in EagleCAD, but just you will have to have a basic knowledge of what those symbols mean. It's like this is a resistor, a transistor, I think specifically NPN, capacitors, and also we spoke about polarized capacitors. Now, capacitors, we just stop working. Right. So we spoke about capacitors and polarized capacitors and polarized components. And polarized in this case just means that the component you are using has got a specific direction in which you need to connect it, meaning that it will have a positive and a negative side. So you will have to connect it in the correct way. Either the component does not work, or it's kind of just gets damaged, which will happen to a lot of the electrolytic polarized capacitors. And also integrated circuits, they have their specific pin configurations, which you will have to connect in the correct way. And it is something you will need to be aware of when you're designing a circuit. Am I using a polarized component? And am I connecting it in the correct way? All right, and I'm sharing my screen once again. And then we spoke about the common electric variables, which we will be dealing with. Voltage, current, power, inductance, capacitance, and resistance. So these are the basic elements that our circuits are made up of. And these are elements that we will need to know how they work for us to be able to successfully design our circuits. We spoke about series circuits and how we calculate these specific values. And then we also spoke about parallel circuits and how to calculate these, and that we will be calculating these values via simulation in Eagle, but you will have to be able to calculate these values by hand. And it's an important point to make that even though we've got a very, very very good software that can do a lot for us, you as a designer and as an engineer will still have to understand how your circuit works and how the simulation gets those gets those values. Because you might have created an error in the design. The simulation doesn't know that you've created an error or a false design, and the simulation values are off, and then you will have to find out what is going on. Or the simulation gives you the correct values that you're expecting, but when you build the physical PCB and you take your values, they do not work, and then you will have to understand where the error might lay or do the troubleshooting or the fault finding. And the programs, even the best programs in the world, are not good enough to help you. You will have to understand what your circuit does, what you are expecting over certain component values. And the program is very, very helpful, but is not the answer to all your problems. Right. We spoke about the prototyping process, starting with as we spoke about, starting with a schematic drawing of a circuit, then calculating some basic values and then simulating the circuit, then moving on to a breadboard. You can create your circuit in a breadboard just to test it out. Then moving on to a strip board or a variboard. And then soldering your components to the variboard, and then finally moving on to a PCB. We also spoke about the soldering process, about how you should be able to do that by hand, and then also as you get more advanced or more, you have to create more, like thousands of these PCBs, then you will probably have a machine like this pick and place machine do most of the components for you. And we spoke about different forms of printed circuit boards. As I said, your printed circuit board can also take the shape of the device that you're creating the printed circuit board for. Now, this is very because it can be a very, very stiff and also very strong material, meaning that you can create it as a structural element of your device. Here on the left side, I like using this because it is basically the whole phone is made up of a PCB, and the plastic around it is just to protect the PCB, but the rigid form is given by the printed circuit board. Then we spoke about creating printed circuit boards. I spoke about using the manual method where you have a transparent piece of plastic where you print onto that piece of plastic your circuit board and then transfer that with heat to the copper and then submerging that piece of copper inside of a acid bath, and then that acid bath eats away all of the copper that is not protected by your printout or by the print. Now, I think on the internet you can buy sort of like these DIY kits to do this, to create your own printed circuit boards, but it is relatively dangerous because you are working with acid that dissolves copper. So it is not good for your hands, for your skin. If the acid falls on it, it will burn it and it'll be very, very bad. And also the fumes from the acid as it dissolves the copper is also not good for you inhaling it. And nowadays, it is actually cheaper to have your design created for you, and you do not need to create the circuit manually by yourself. The only reason why I'm talking about this in such a way is that to demonstrate that it is possible to create this at home without any real specialized tools, but it is probably not necessary. And like I said, traditionally, well, not traditionally, but nowadays, it is more feasible and probably easier and cheaper to send it off to a company which might manufacture it with a certain amount of machines. We spoke about milling machines that uses very, very small drills that drill out your circuits from a blank of copper. And what it basically does is, as we spoke about, it isolates the circuit, milling away or removing the copper on either side of a trace, isolating it, and therefore creating a circuit. Now, this can be a drilling machine, a laser machine, or an industrial etching machine where the process with the acid removing the copper is done in a bigger machine and as an automated process. Usually when you have thousands or hundreds of PCBs being created, the company where you will have sent your boards to be done, or your specific company doing it, will use an industrial etching machine like this. And we spoke about multiple layers, meaning that you will have your printed circuit board can have several layers. The main layer is the front layer and the back layer, meaning on either side of the PCB, there might be copper or there might be a circuit. And usually on these front layer and back layer is where we attach our components. Now, in between these two main layers, there might be other sub layers. And these are mainly used to facilitate the connection of your components on your front and your back layers. And we do that if we have very complex components, like a component with a ball grid array. If you have a PC or a CPU processor, that's relatively small, but it has got, 80 connections in a grid at the back, then you will have to have some sort of hidden layers that will facilitate in the connection, where your circuit board is created or connected within sub layers inside of your PCB. And then we spoke about if you have a PC motherboard, it can have anything from 6 layers up to 14 layers. There might be more, depending on what CPU or what motherboard you have or what PCB it has, there might be more. Now the Eagle we're going to be working with, because it's a free version, we only have 2, which is more than enough for our processors. How would I know if I need more layers? Well, when you are connecting your components, or you run an auto routing program, which we will be looking at. Auto routing means that if you have your printed circuit board program, it will try and connect or create the traces for you. And then it will tell you, I cannot do this task, it's impossible, we have to add in more layers. Then it adds in more layers automatically and connects these components via themselves. But that is also something we will look at, multi-layered boards, as we call them. But usually for the purposes of this course, a double-sided board is more than enough for this. But adding in multi-layered boards is really not that difficult. Mostly the program or the auto routing software that almost every printed circuit board design software now has would be able to do this for you. Right, I've shared my screen again. And we also spoke about solder masks, which is the green resin that protects your copper traces. And then these are called pads. That is the exposed electrical connection where you will then be soldering your components on. This is what we call a silk screen. It is a printed information that is printed on top of your solder mask, and it just gives information about the components that you would be creating on your printed circuit board. Usually you will have some sort of revision number. In this case, this will be revision 3.1. So what is a revision number? Well, if you have created your circuit for the first time, you've created your printed circuit board, usually that will be version 1. Now, through testing or through other processes, fault finding, you might change the design of your circuit, either the connections, or you might substitute some components. Some components might not be available anymore, or some components will not work as you expected, and then you will then replace them on your circuit board, meaning that your design will change. Then the change in design, the new design will be revision 2, for instance, or revision 1.1, depending on how extensive the changes are. And you usually indicate that onto your printed circuit board, which revision that specific design is. Now, why do we do that? It all has to do with maintenance. So when you create these boards for a customer, usually somewhere down the line, some components might break. When you will have to fix it, you will then have to first establish which circuit board you're working with, i.e. which revision. You will have to, then you'll look at that design, you'll look at the documentation that you have created for this design in terms of what the board is supposed to be doing, what components you're using, and that will be indicated by the revision of the board. Usually, most of these boards would have some sort of title. In this case, it's a PIC user interface. I'm not exactly sure. And then it will have information about the components. Now, the information about the components solves a couple of problems for us. Firstly, you might be designing the board, but you might not be the person assembling this board. So that after the board has been manufactured, it gets sent to a person that would assemble the board or insert the components. And they will then look at the markings of the board, let's say SP1, look at a sheet or a table, see what is SP1, what component is it, select that component and insert it in the place designated by SP1 or Q1 or R2 or whatever. Usually R2 is indication of a resistor, or R is indication of a resistor, C is capacitors, SW is for switches, but that is mostly for you to decide what that means. Right, so this is called a silk screen, and when you send your design away to a specific manufacturer, you will then designate if you want a silk screen or not. But if it is a design that will be manufactured in great numbers, you will have to, a silk screen becomes almost a necessity. We spoke about components, different types of components. Mostly what I wanted to focus in terms of this is that we deal with linear and non-linear components, but more we deal with ideal and real components. So in the simulation and also inside our calculations that we do, we deal with something called ideal components, meaning that the components behave in a predictable manner. They are easy to work with. They behave perfectly. But in reality, that is not how they actually do or how they actually operate. The performance of your components can be affected by so many environmental effects. And we spoke about heat is a big one, which changes the resistive properties of elements. But it might also be, and I'm sharing my screen once again, I'm getting to the slide. It might be pressure, moisture, interference from other sources, noise, and so on and so forth. So when you are creating your circuits and you're testing them, and the results deviate from your expected simulated results, just bear in mind that most of the time it has to do with the ideal components not having the exact same performance as the real actual components. So that is why we create simulation to check our design. We prototype in limited numbers to check our design even further. And once we have tested everything, then we move on to our final design. And then we spoke about surface mounted and through hole, the two main type of components that we get. We'll also have a look at a couple of components. The difference between surface mount and through hole. And as I spoke about, the surface mount or SMD are components that are totally comprised on one layer. So this will be the front layer. Here on the right side is the front layer, and that will be all my components on that front layer and none of the components penetrating through to the bottom layer. Whereas with through-hole components, the physical component is on the one layer, but they penetrating through the board and are soldered and connected to the circuit on the back layer, for instance. Then we spoke about the types of components, and we focus more on resistors, capacitors, and inductors. And we all are relatively, hopefully, comfortable with designating or finding out using the 4-band code, or how many bands you would have on your component to find out what the resistance and also the tolerance value is. And also on SMD, they also have markings, and these markings also designate what the specific value of these components. Then we spoke about conductors. Wherever you see a coil, meaning copper wire that is wound around a conductive element, you will know it is a coil, and it performs a couple of very important electrical tasks, the same as capacitors. And all these components come in their own surface mount or through hole variants. And then we spoke about the different integrated circuits and how these circuits, as with every other circuit, come in different packages. Now, packages are the physical standardized shape of the components. This will be C-dual inline package, so a C dual inline package. DIP usually stands for dual inline package. You can also have SIL, single inline package, just meaning you have a single row of pins, or a DIP, dual inline package, which have dual pins running through it. And then we also spoke about connectors and how these are essential but often overlooked components, because usually your board needs to connect to something on the outside, and those are always done with connectors. Usually if you have connectors that plug something into the outside, like this specific VGA connector, it would have some structural connector that is, or structural element that is not connected to the physical board itself, but they are connected through holes just to produce stability. And this is an important element as well. If you have, let's say, nowadays a USB connector is more relevant or more prolific than let's say one of these old VGA connectors. But anything that you expect the user to plug into their PCB and then plug out, as with most mobile phones, that USB connector would have some structural element that is physically connected to the board. And I'll hopefully, with the microscope, we can look at that and you'll understand what I mean. But if you plug in something, it cannot be just connected with the physical connections to the board or the physical connection to the traces, because that is a relatively weak connection with the soldering and the copper. And through time, if you plug in and plug out, the connection might degrade. the connection between the component and the copper connected through the solder. Remember, that is a very hard, non-flexible connection a lot of the times. And if the component moves, that joint, as we call it, will become deteriorated, and it'll crack and then break. And then as time goes on, or the movement goes on, it will separate the connection and the board will lose some of its functionality. So when we have a connector where you plug in things, plug in and plug out, quite often there's some structural non-electrical connection to that connector. And then we spoke about different elements of CAD. We spoke about why we are using EagleCAD and KiCad, Multisim, and Proteus, and also there are lots and lots of others. And then I showed you a couple of examples of printed circuit boards. Single-sided, double-sided, multi-layer, and then boards can also be slightly flexible if that is something that you would need. This is an example of a multi-layered board, and every single one of these colors represents a different layer of a board. Now, this is just an exercise that somebody did to see how many layers they can actually use. I'm guessing that they actually do not need to have this many layers connected, but this is just an example. Usually 2 layers for us is more than enough for the type of components that we are using. And when we are creating circuit boards or creating the PCBs, every single layer is denoted by its own color. In this case, blue is indicated by the back layer and red for front. But we will have a look at this as we are creating our PCBs. And then your PCB does not need to be in a square as is traditional, or you might have seen printed circuit boards. They can be any shape that you require. Also, your components do not need to be necessarily inside of a grid. They can also be at different angles, which we'll also play around with in our printed circuit boards. And then we spoke about flexible PCBs and looking at manufacturing, and then that is done. So in this very short half of the class, we ran through all of our theory, which we spent, I think, 3 periods last week looking at. So now hopefully we're all refreshed. We all know exactly what all the theory is. And after we've taken our short 5-minute break, so I need a drink of water, we will look at some examples of the printed circuit board through my little microscope, which is luckily working. And then we'll start looking at EagleCAD. Like I said, there are printed circuit board design can be a very simple process. And then as you get better, you are able to create more and more complex designs. But a lot of the times the software is really good at validating your design. What does validation mean, or validating a design? It means that it performs a couple of tests on your design and then tells you if there are a couple of problems, in which we'll also look at the validation of your design. But I keep on stressing the point, even though the software is really good at the task that it needs to do, it is not perfect, and you will still have to validate your own design. Or if the validation fails, you will still need to know why it fails and be able to fix it by yourself. Because software nowadays, it's very good and intelligent, but most of the time, if there's a problem, it will not tell you what the problem is. Right. Let's take a quick 5-minute break, have a drink of water, do what you need to do, and then I'll see you again in about 5 minutes.